1.6 Packing of particles in crystal lattice. Constituent particles of an crystalline solid are close packed. While describing the packing of particles in crystals, the individual particles are treated as hard spheres. The closeness of particles maximize the interparticle attraction. The number of neighboring spheres that touches any given sphere is its coordination number. Magnitude of the coordination number is a measure of compactness of sphere in close packed structure. The larger the coordination number, the closer are the sphere to each other. 1.6.1 Close packet structures. The three-dimensional closed packet structure can be understood conventionally by looking at the closed packing in 1 and 2 dimensions. A. Closed packing in 1 dimension. A closed packet one-dimensional structure results by arranging the spheres to touch each other in a row. Refer figure 1.3a. B. Closed packing in 2 dimension. A closed packet 2 dimensional planar structure results by stacking the row together such that they are in contact with each other. There are two ways to obtain close packing in 2 dimensional: square close packing. First, square close packing. In 1 dimensional, row of close packet spheres are stacked over each other such that the spheres align vertically and horizontally. Refer figure 1.3b. If the first row is labeled as A type, being exactly same as the first row, the second row is also labeled as A type, hence the arrangement is called A, 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 dot dot dot. Type 2 dimensional arrangement. In this arrangement, every sphere touches 4 neighboring spheres, hence 2 dimensional coordination number here is 4. A square is obtained by joining the center of these 4 closest neighbors. Refer figure 1.3b. Therefore, this 2 dimensional close packing is called square close packing in 2 dimension. Second, hexagonal close packing. Close packet 1 dimensional row figure 1.3a show that there are depression between the neighboring spheres. If the second row is arranged in such a way that its sphere fit in the depression of the first row, a staggered arrangement result. If the first row is called A type row, the second row being different is called B type. Placing the third row is staggered manner in contact with the second row give rise to an arrangement in which the sphere in the third row are aligned with the sphere in the first row. Hence, the third row is A type. Similarly, sphere in fourth row will be aligned with the sphere in second row, and hence the fourth row would be B type. The resulting 2 dimensional arrangement is AB type. Refer figure 1.3b. 1.3c. In this arrangement, each sphere touches six closest neighbors. Thus, the two-dimensional coordination number in this packing is 6. A regular hexagon is obtained by joining the center of these six closest sphere, figure 1.3c. Hence, this type of two-dimensional close packing is called hexagonal close packing in two dimensions. Compared to the square close packing in two dimensions, the coordination number in hexagonal close packing in two dimensional dimension is higher. Moreover, the free space in the arrangement is less than in square packing, making it more efficient packing than square packing. From figure 1.3c, it is evident that free spaces voids are triangular in shape. These triangular voids are of two types. Apex of the triangular voids, alternative rows point upwards and downwards. C. Close packing in three dimensional. Stacking of the two-dimensional layer gives rise to three-dimensional crystal structures. Two-dimensional square close packed layer are found in stack only in one way to give simple cubic lattice. Two-dimensional hexagonal close packing layer are found to stack in two distinct ways. Accordingly, two crystal structure, namely hexagonal close packet HCP structure and face centered cubic FCC structure are formed. First, stacking of square close packet layers. Stacking of square close packet layers generates a three-dimensional simple cubic structure. Here, the second layer is placed. Here, the second layer is placed over the first layer, so to have its sphere exactly above those of the first layer. Figure 1.4. Subsequent square close packet layers are placed one or above the other in the same manner. In this arrangement, sphere of all the layers are perfectly aligned horizontally as well as vertically. Hence, all the layers are alike and are labeled as A layer. This is arrangement of layers is described as AAAA type. The structure that result on stacking squares close packet layer in simple cubic its unit cell in the primitive cubic unit cell, figure 1.4. It can be seen that the simple cubic structure, each sphere touches six neighboring spheres, four in the own layer, one in the layer above and one in the layer below. Hence, coordination number of each sphere is 6. Polonium is the only metal that crystallizes in simple cubic closed packet structure. Second, stacking of two hexagonal closed packet layers. To generate a closed packet three-dimensional structure, hexagonal closed packet layers are arranged in a particular manner. In doing so, spheres of the second layer are placed in a depression of the first layer, figure 1.5. In the first layer is labeled as A type layer. The second layer is labeled as B layer. Because the two layers are aligned differently, it is evident from the figure 1.5 that all triangular walls are of the first layers are not covered by the sphere of the second layer. The triangular walls that are covered by spheres of the second layer generated tetrahedral world. A tetrahedral world is surrounded by four spheres. On joining the center of of these four spheres, a tetrahedron is formed, which encloses the tetrahedral walls. Figure 1.6. The remaining triangular walls of the first layer have above them the triangular walls of the second layer. The overlapping triangular walls from the two layers together form an octahedral walls, which is surrounded by six spheres. Figure 1.7.